Okay, molecular term symbols. Let's do it. So this is going to be very similar to atomic term symbols. However, we're going to really rely on MO diagrams to get the correct term symbols, okay? And in this, I don't even really like to bother with the Klepsch-Gordon series here, because if we can use our MO diagrams, and including MO diagrams for the excited states, I think it's much more straightforward. Okay, so multiplicity, the 2s plus 1, that has its usual meaning. Instead of a capital L, like we use for atoms, we use a capital lambda for molecules, which is still representing our total orbital angular momentum quantum number. But now we have a new term right here, which is related to symmetry. And so this parity, right, that's all about the G or the U symmetry operation. So that turns out to be more important to notate in molecular term symbols. Okay. So lambda can take on values 0, plus or minus 1, plus or minus 2, etc. Okay, just like L. And the absolute value of lambda is what we're interested in. And so when that's a 0, it's a sigma. And that's analogous to when L is a 0 for atoms, it's an S. Okay, so there's that connection still there. When lambda is 1, it's a capital pi. And when lambda is 2, it's a capital delta. So how do we get these lambda values? All right, well, lambda is the sum of all of the little lambda values. All right, easy. And we ascribe, and we're only going to deal with sigma bonds and pi bonds. Okay, so a sigma bond has a lambda equal to 0, or really I should say a sigma electron. Let's be clear about that. These are electrons. Okay. And based on the number of electrons in those respective orbitals is how many lambdas that we will add up. All right. When we have pi electrons, lambda can be plus or minus 1. And it's arbitrary which one we pick as plus or minus 1. But what's important to note here is if we put something in the pi x, we'll call it plus 1. And if we put something in the pi y, we'll call it minus 1. I could switch these if I want to. It's arbitrary. But what's important is, however I decide I'm going to do it, if I call pi x plus 1, I have to call pi y minus 1. Okay, that's really important. And I'm going to go through several examples. Okay, so let's look at H2. And I'll remind you, H2, I'm not going to do the MO diagram because we remember, hopefully we remember, it's a very simple 1 sigma G2 is the molecular electron configuration of H2. And actually, let's just go ahead and, I can back it up. Right, here it is, my H2. So 2 electrons in the 1 sigma G, so it's a 1 sigma G2. Okay. So when I'm going to add up all of these little lambda values, I'm going to ascribe, so I have 2 electrons, right? So I need to come up with 2 little lambda values. And because they're both in sigma bonds, each one is going to be a 0. So that's a 0 plus a 0 to equal 0, which is a sigma. Okay, great. Well, what about nitrogen? Okay, so let's go ahead and quickly take a look through its MO diagram. Oh, here I've got it right here. Okay, lovely. So in nitrogen, all right, I'm predominantly interested in the valence shell. So remember here, my 1 sigma U and 1 sigma G, that's making up my core electrons for this period, right? For this period, the 1 sigma G and 1 sigma U is the core. Once I start at the 1 pi U, 2 sigma G, etc., that creates the valence shell. So I'm going to add up all of these for the valence shell. And let's go ahead and note that nitrogen's valence shell is 1 pi U 4 2 sigma G2, right? So there's 4 electrons in the 1 pi U and 2 electrons in the 2 sigma G. But we have to remember, okay, the 1 pi U is technically broken up into 1 pi x U, and we could say there's 2 of them there, and 1 pi y U, and there's 2 of them there. So that's where we're going to see this plus minus 1 situation. Okay, I just want to check something really quickly. Okay, good. So now what we can see with nitrogen, so let's write that down. We know that it was 1 pi x U 2, 1 pi y U 2, and 2 sigma G 2. Okay? So now I'm going to do all 6 of these electrons for my lambda. And like I said, it doesn't matter if we pick plus 1 or minus 1 as long as we're consistent. So I'm going to pick plus 1 for the x. And that's going to go plus 1 because I've got 2 electrons in that pi xu. Well, now I've got 2 electrons in the 1 pi yu. So that's going to be a minus 1 and a minus 1. And then now I've got 2 electrons in the sigma. And sigmas get a 0. So that's a plus 0 and a plus 0. And lo and behold, that all equals 0. So N2 is also a sigma state. Okay. So let's see here. So what's coming next? Yes, let's keep